All right, surface integrals. So 16.4, starting out with Maddie and Madeline. All right, they're plugged out. Surface integrals, we know that a surface, that surface is going to be in three-dimensional space, so we have three variables. So the thing that changes with our parameterization is now, we usually can't express three variables in terms of just one variable. So what we do is we just express that third variable in terms of two other variables, and that becomes our parameterization. So, so consider like this surface here, or like this surface here. When you parameterize it and you take the partials with respect to u and v, or x and y, or like a and b, whatever you call your parameters, like we remember from chapter, I think it was like 15 or something, that the partials are pretty much just like at that point, what is the tangential like vector along that line, like in that direction of the partial? Does that make sense? Do you remember that? Kind of vaguely. All right. So the only reason I mention that is because of this kind of like visual representation, which I think really helps, where you have your partial going along in the u direction, your partial going along in the v direction. Those are just like the variables that I choose to call my parameters. You can call it anything you want. And so what you effectively have now is just two vectors like that are tangent to the surface. Are we up to speed so far on that? We're good on that? So then when we cross those, we're going to get a normal vector, right? And something that Abhishek mentioned that Beck's section went over, which like maybe section didn't, which is actually really helpful to understanding like what are we actually doing with these surfaces, is going back, like I think back to chapter 12 or 13, when we first started learning about like vectors and cross products and stuff, and looking at what the cross product means. So we know that when we cross these two vectors, we're going to get a normal vector. That's nothing new. But something that is kind of like, dusting some cobwebs off is what the magnitude of that normal vector is, or what the magnitude of the cross product is. We know that every like two vectors, if you like add them together and subtract them and stuff, we get a parallelogram. Is this like ringing a bell? It should be vaguely familiar. Yeah. We know that if we do the magnitude of the cross product, we get the area of the parallelogram. Does that make sense? So if we look at this kind of like zoomed in picture, this parallelogram isn't exactly matching the surface, because like there's some curvature to it, and the parallelogram just like a little sheet. But as we like shrink this down, like and zoom in farther and farther, that curve is going to look more like a flat plane, or it's going to look more like a parallelogram. And because we can find the area of each one of those little parallelograms, and we can add all of them up across the surface, that's pretty much what we're doing with surface integrals. So this is
Wait, repeat.
This is did we all catch that? Do we want to go over it one more time?
Yes.
Well, I guess okay, one more time. So like a surface integral, we have a surface and it's like curvy, it has like contortions to it and stuff. But if we want to look at just one little tiny speck of it, because like I said, with all things integration related, we're breaking it up into little pieces and adding all those little pieces up with each other. When we're looking at just a little piece of the surface, if we evaluate the partial with respect to u and v, or the partials with respect to your parameters, those two variables that you chose, what you're going to get is two vectors pointing, in like, I think they should be 90 degrees apart from each other unless you did like some really weird parameterization. But that doesn't really matter, because when you cross them, you're going to get a normal vector, right? And we know that these two partials are tangent to the curve, or tangent to the surface, sorry. So tangent to the surface, and you cross those two together, you're going to get a normal vector that is orthogonal to the surface. So we know from previous sections that if we take the magnitude of the cross product, or the magnitude of the vector, we're going to get the area of the parallelogram made by the two vectors that were crossed. And in this case, those two vectors were the partials with respect to each parameter. So what that means in terms of like, so let's put that into the bigger context of what a surface integral is. we now know what the area of a little tiny speck or a little like parallelogram of a bigger surface is. So now that we know that little area of the surface, just like we knew the little arc length of a line, we can add all of those up. Does that make sense? Mm-hmm. And now we've like effectively covered the entire surface. So kind of going off of that more, if there was just a problem that said find the surface area of this curve, of this surface, of whatever it is, what you want to do is literally just integrate the magnitude of the normal vector. Because if you think about that, what I've said in the past few minutes is that when you're integrating it, what you're doing is you're adding up each one of those little like areas, each one of those little parallelograms. Yeah. Because the orthogonal vector, that normal vector, is the cross product between the two partials, right?
So you're taking the magnitude of
yeah. Yeah, because we know from like chapter 12 or 13 that the magnitude of the cross product equals the area of the parallelogram made by these two partial vectors, or not partial derivatives that are vectors. And if you think about like, okay, so what is the domain that I need to integrate on? What you kind of want to do is, in this picture, I feel like that's a good job of visually describing it. You're going to want to project that down to some axis so you just have a two-dimensional domain. And then if you think about, this picture in the context of this picture, what you're doing when you're integrating along the x-axis or y-axis, or whatever parameter you chose, you're adding up all these little parallelograms in one direction, so kind of like making a line. And then the second part of that integral, of that double integral, is adding up all those little lines in the other direction. So you're like covering the entire surface. Does that make sense? And like if all those little like areas of the parallelogram added up, because like when you integrate it, they're infinitesimally small, so they equal the area of the actual surface. That's how you find the surface area. And then also keep in mind, even though I've like been talking a lot about this in like a vector interpretation, what we've done so far, the function that they gave us wasn't a vector field. It was still a scalar function. So you can think about like everything I've said in the past like 5 or so minutes as kind of analogous to a scalar line integral, but as like a scalar surface integral. I know that's kind of confusing because like I've been talking a lot about like vectors and cross products, but hopefully that makes some sense. So taking that a step further into now that we know what a surface integral is and where it came from and how to not just like only memorize the formula, but to understand like what's actually going on in the formula, we can, just like we did with the line integral, we can add another variable in there or another function to give that surface integral more meaning. So that's where you have this function of like x, y, and z. Just like what Abhishek was saying with the curtain example for a line integral, where that function signifies the height of the curtain. It's the same thing here, where somewhere along the surface at this specific point, there's some kind of special meaning to it.
Like a temperature.
Yeah, like a temperature. Or if this was like a curve that represented a hill or a mountain, and each one of these little like parallelograms represented like a sector, and the function represented like a population density or something, that's what I'm talking about when I say it takes on a special meaning. Does that make sense? So when you look at the surface integral formulation to find surface area, and then the actual surface integral that we're going to be dealing with, the full expanded formula is right here, where you have this function f of x, y, z, and you're integrating it with respect to ds, capital S. And what that ds is, the way that I think about it, is just like a little surface, or like a little patch, right? Like a little bit of like this little parallelogram. And you're adding all that together. So in terms of like a third, not third variable, like a function that gives each one of these little pieces meaning, how it looks in the integral formulation, you're just multiplying by that function. But just like we did in line integrals in 16.2, we're only concerned with that function as it applies to the surface. That's why we plug in our parameterization, g of uv, that could be like h of xy, depending on how you parameterize it. That's why we're plugging that into the function they give us, because we only care, what does this function look like on this window that is my surface. Does that make sense? So like draw your own parallels, but I kind of think of that analogously to like scalar line integrals. Do you have a question?
Yeah, so with the surface area equals that integral thing, are you saying that's the same thing as that surface integral there?
Yeah, all right, so this is like a special case. Yeah, that's a good observation to make.
Is that only if they give you like points or like, no, like
Oh, no, so I'm gonna address your first question. So the surface area, this like formulation, this like comes from the fact, or this comes from this function equaling 1. So if this function equals 1, what we're like pretty much saying in like a visual or conceptual interpretation is each one of these little surface areas doesn't have any special meaning ascribed to it. It like literally is just a little surface area. So when we add it all together, we're going to get the surface area of the entire surface. Does that make sense? Awesome. Do we have any other questions on just like surfaces in general? Yeah.
Is that the only time you're ever going to integrate in terms of 1? Function being 1?
I'm sorry. Oh, yeah.
Is this the only time you will, or you will integrate 1 as the function, and then every other time you're going to be given some kind of vector, function vector, or?
So I don't think that they're going to actually like say f of x, y, z equals 1.
No, right,
but
is this the only, for a surface integral, is the only time you integrate 1?
To find the surface area?
Yeah.
I'm going to go ahead and say yes. I can't think of any other.
Never mind.
No, that's a
I've
valid
asked
question.
maybe the same question.
Wait, what do you say?
He doesn't, no one knows what I'm asking. Like, I don't know how it'll work, but I'm trying to ask.
The only
No one
reason you make that
understands.
one is for the surface area.
That is
Yeah.
the only time.
Yeah.
Okay, that was the question.
You only pick the function as 1 if it's like you find the area of anything. It's always gonna be 1, like volume. So it'll be 1.
Yeah, do you remember like we did like half an entire lecture on like what double and triple integrals mean? And he said that if you do the triple integral of some region or some like region W and you let your function equal 1, then what you're doing is you're finding the volume. It's kind of like that, where if you set it to 1, it doesn't have like an extra meaning to it. You're literally just finding the length or the volume or like the area. Does that make sense? Hold on, I'm gonna take Zach's question.
Wait, so what are you finding when the function is not equal to 1?
Okay, so when the function is not equal to 1, if the function equals like, I don't know, like let's say the function was in terms of like x, y, and z, and it was like x e to the negative zy x times some constant or something, that function they give you is going to mean something. They'll say like, find the charge, the total charge across the surface. And then that function is going to be a function modeling what the charge is at each one of these points. Does that make sense?
Okay.
Okay. Do we have more questions on surface integrals like its scalar form? All right. So just like we did in 16.2, where we have scalar line integrals and vector line integrals, the next kind of like application of surface integrals is surface integrals with vector fields. So, all right. So if we go back to the objectives, going back to 16.4 really quick. Parameterizing a given surface, we've done that. Determining the equation of a tangent plane to a parameterized surface, I'm going to touch on that in like a few minutes. Calculate the surface area, we talked about that. Calculate the general surface integral based on a parameterized surface. That's the calculate the surface integral if they give you a function. And like that function's not equal to 1. So you're not just finding the surface area, you're finding some kind of special meaning in terms of that function across an area. So then, going back to 16.5, now that we have directions associated with our vector fields, because they're all vectors, they'll ask you like calculate the flow across this surface or something like that. And what you need to kind of like organize in your head is that when we did vector line integrals, we were looking for the vectors that were tangential to the line. For surface vector surface vector integrals, I'm not sure if that's how they actually say it, but for surface integrals involving vector fields, we're looking for the vector components that are not tangential to the surface, but normal to the surface. So we want to know, like, imagine if there's like a screen here, and I was like, and I threw my pencil through it at an angle, I would only be concerned with the part of that vector that is directly normal to the surface. One of the WebWork problems was like kind of weird. It was like the 4 squares and there were dots on it and stuff, and they gave you the normal vectors of all of it. So for that one, like because it was an XY plane, the normal direction was just the positive Z direction. So that's why you had to like average only the Z components. But we're talking just in general with surfaces. So does that make sense in terms of like a vector field along the line, we want the tangential components, and then a vector field along the surface, we want the normal components? Okay. So, oh shoot, where was I? So for 16.5, the formula is like pretty much identical to the formula for 16.2 for a vector line integral, where you have your vector field, and you only want to investigate that. Vector field on that surface. So that's why you plug your surface parameterization G of UV into your vector field. Does that make sense? Cool. And then again, because we have because we're dealing with vectors, we're going to do the dot product to like combine those two things together. And in vector line integrals, we were doing the dot product of just the derivative of your curve. So like just the tangential piece of it. This time we're dotting it with the normal part of it. So like think surfaces, surface integrals and vectors, I want the normal component, and then lines and vectors, you want the tangential component. So again, with vectors having magnitude and direction, they're always going to specify upward is the positive direction or downward is the positive direction. So think about this, if this were the surface and all of these were vectors, if they specified that upward is the positive direction, these 4 vectors here passing normal to the surface would give you a positive number, because like that's how they defined the like the orientation. But if they said like consider downward as the positive direction, then the sum of these 4 vectors would give you a negative number. Cool. So just really quick on like how do you actually do that, kind of putting it into like a 5-step process. You're going to parameterize the surface, and that's just expressing 3 variables in terms of 2 variables. And you can do that a number of ways. We're going to practice that. You find the normal vector, which is just crossing the u partial and the v partial, or like the partial with respect to your parameters. You do the dot product to kind of like put that, to put like your function that has some kind of meaning to it, along with the little like patch of the surface you're dealing with. You're doing the dot product, you're putting those 2 things together, and then you're integrating. You're adding up all those little bits together. Does that make sense? Cool. Am I missing anything? Yeah. All right, so going back to 16.2, talking about tangent planes. I don't really have like a visual representation of this, but actually we can use this again. One of the questions that is like a really good question, it wouldn't surprise me if it was one of the questions on the test tomorrow, is determine the equation of a tangent plane to a parameterized surface at a given point. So for those types of questions, going back to what I was saying about your partial with respect to your parameters gives you 2 vectors, and you do the dot or the cross product of them, and it gives you a normal vector. We know from chapter 13, dealing with like tangent planes and partials and stuff, that the normal vector, if we know a point and we know a normal vector, we can find the tangent plane. right? So that should be ringing some bells right now. So in terms of what that actually looks like, in terms of actually finding the equation of a tangent plane, what you're going to have is your normal vector will be, I'm just going to say the x component is going to be A, the y component is going to be B, and the z component is going to be C. So like whatever your normal vector is, those components become the coefficients of your x minus x naught, y minus y naught, z minus z naught, where x naught, y naught, and z naught is the point that you know. So if they asked you find the equation of the tangent plane to the paraboloid z equals 1 minus x squared minus y squared at the point 1, 1, 1, that point 1, 1, 1 would be the point that you know. And then finding the normal vector at that point is just a matter of doing the partial with respect to u and v at that point, doing the cross product, and then plugging in the components of the cross product into this like tangent plane formulation. Zach,
And
sorry.
does it matter which point you use to plug in into the tangent plane equation?
Well, it has to be the point that they want you to find the tangent plane.
So that point, it has to be given.
Yeah, like they can't just tell you like find the equation of a tangent plane to the surface because like there's an infinite number of tangent planes.
Okay.
So they have to tell you at this specific point.
Okay.
Cool. All right. So that's pretty much like all of chapter 16. Do you guys have questions? Zach?
If would there be like, if they ask you to find that point, like if they give you other points, and, never mind.
Oh wait, are you talking about like if they said if this is the equation of a tangent plane to the surface, what point is it at or something? Because that would be like that'd be a bitch of a problem.
It's not that bad.
All right, well if you're V-shaped Gupta, it's not that bad, but.
What?
More questions, chapter 16, Dan?
So there's like all the different types of parametrization for line integrals.
Yeah.
Are there more than one really for the surface integrals?
Yeah, all right, so for the surface integral one, we talked about like if you have z as a function of x and y, just let x and y be your parameters.
Right.
But something that he was talking about in class with like that lampshade example, if you know that, I actually like didn't prepare anything for this, so I don't have like visuals to go with it. But if you have, for instance, a cone, and they give you the equation of a cone, which I don't know it off the top of my head, but let's say that they give you that, and they say, sure, and they say find the surface area of this cone enclosed inside some bigger cylinder. So if you think about like cylinders and cones and like they make circles and stuff, the parameterization you're going to use is cylindrical coordinates. But you have to keep in mind that the only thing that's going to change as you go up and down this cone is the radius of the circle. Does that make sense? So that's the whole like you can use polar, cylindrical, and spherical if you know that one of those variables is constant. So like another example of that would be so let's say the surface was just a half hemisphere. And they give you like the equation for it. It looks like really ugly, and you know that the integration is going to be like horrendous. So you can convert that to spherical coordinates because you know that rho is constant. That the distance from the origin of this hemisphere is all the same. So when you're thinking about like how let's kind of parameterize this, try and like think about it like visually about is there some kind of like variable that I can freeze, so to speak, that like doesn't change? And if so, you can just plug that in as the constant that it is. Cool? Awesome. Okay. So that's pretty much all of chapter 16.